recording now. Fine. Right. So last week we were looking at, especially the last class, we were looking at a lot of techniques for model compression, and we approached the same problem from different aspects, whether you were trying to distill a smaller model or maybe deleting unnecessary weights or maybe redundant weights within the model, or maybe even optimize or sort of quantizing the values or the parameters that you are storing for corresponding to the weights of your network. And I think we missed one of the terms that was basically a lightweight model design, which by default it's not model compression as such, but you reduce the size of your model by using architectural elements itself, which are maybe lightweight or maybe which allow you to have sort of the same performance without increasing the size of the model too much. So there are many such techniques. We'll briefly discuss on this, and then we'll start up with the next concept of neural architecture such. So the very famous model name whenever you hear about any lightweight model design is the concept of, say, MobileNet. You have, say, V1, V2. I think there are also follow-up models now. So we'll just briefly discuss the ideas behind what architectural components they included to make their network design itself very lightweight. Specifically, if I look at the MobileNet V1 model, what they tried to introduce was the concept of a depth-wise separable convolution. So generally, when you think about any convolution layer, you have a filter of, say, size 3 cross 3. Okay, but it's whenever you're applying it to any image of, say, an RGB image of, say, you have, say, 100 cross 100, and you have, say, 3 such channels. So you have RGB channels. Your convolution is actually not 2D. The filter is not 2D. It's actually, this has to be multiplied with all your input channels. So at the end, if you have 3 input channels, you actually are doing 3 cross 3 cross 3 learnable parameters at that particular level, and that is for a single filter. Now, if you have, say, 10 such filters at that particular layer, you will have 10 such set of filters, all of size 3 cross 3 cross 3. Okay. So, but the point is that whatever 3 cross 3 filter you choose, it always gets applied to all the input channels. So in this case, if you have 3 or say 10 input channels or 100 input channels, you will learn basically an entire filter of that many, at least depth dimension will match the input depth dimension. So what depth-wise separable, this obviously introduces a lot of parameters. So if you're thinking about using a 3 cross 3 parameter, 3 cross 3 filtered convolution, ideally we were thinking about, say, parameter of size 9, but because it uses the entire depth, it considers the entire depth of your input as well. So you end up with, say, 9 cross 3, which is 27 learnable parameters, which the target of the creators of MobileNet was to reduce these usage of, reduce the number of parameters that you're using, so that your model itself becomes lightweight. Also, you can maybe reduce some of the computational overheads. And imagine if you had 100 such filters at any given convolution, so you would now have 2,700, say, filters, 2,700, say, learnable weights. So what depth-wise separable convolution does is that you have an input, say, of whatever width and height, okay, but it has some set of channels. Okay, your filter, as we've seen, will be of size, say, 3 cross 3, but it will also have a depth component of size C. Okay. So what it does is that depth-wise separable tries to reduce this thing. So it will try to reduce the scope of every filter. Maybe your filter only gets applied to 2 channels at a time. So in a way, you're trying to reduce the number of learnable filters. That's why it's known as depth-wise separable convolution. You're separating the convolutions in a depth-wise manner. So if you do not allow the filter to be of size 3 cross 3 cross channel, instead, say, you do 3 cross 3 cross 1, that same 3 cross 3 weight will get applied to every channel, irrespective of the height and width. it will be same filter will get multiplied to every channel, and then obviously you have say 10 such filters. So the total number of say parameters, if you have 10 such filters, will be 90, as opposed to if you had this particular setup, you would have had 270, which is less. And if you consider even more such filters, then you can see even much more drastic number of decrease in the number of learnable parameters. Okay, that was one of the innovations that MobileNet brought in through its structure, and in a way it reduces the size. So you can consider it as a say indirect technique of say model compression. You design the model itself to be lightweight. Okay. Another concept which MobileNet V2 built on your V1's concept and brought in another idea, that's the concept of using say 1x1 convolution to actually reduce the number of channels which are given as input to any 3x3 or say higher sized convolution. So if I reduce this number of channels at this phase, again, when I apply a convolution which has more number of say learnable parameters, your learnable parameters can be handled. So explicitly, I'll just show you this thing. So suppose you have an input of say size 100 cross 100 cross say 50. So you have 50 channels. Okay. What MobileNet V2 does is that it will use a 1x1 convolution. Remember, 1x1 convolution will only consider this much area. I mean, just a single pixel in a particular channel. Okay, and then you might have 100 such channels. So you'll have 1x1x100. What you can do is that you can control the number of output filters. So suppose you have only 50, or say in this case you already have 50. So if you only have 10 such 1x1 filters at a particular convolutional layer, you will convert this input basically into again 100 cross 100 cross 10. So what did you do? You did not learn anything in terms of spatial information, but you have actually reduced the size of your input, at least the number of channels in your input, to 10 without directly deleting channels. I mean, the other extreme option is you simply delete the channels. Okay, but instead of doing that, you are using a 1x1 convolution to combine these 50 channels and only output say 10 channels. So if you can do that, what happens is that you then apply say a larger convolution which has more number of learnable parameter. Say in this case you have say 3x3 filter. So in this case, if the depth is 10 and you are again maybe using only say 5, okay, you will not lose out on that much of information which would have happened in the original MobileNet. Suppose you are restricting every channel to only look at 5 channels of your input at a time, which meant that you would have to reuse a lot of same set of parameters for a lot of different channels, which might be harmful because different channels might have different information. So instead, what you're doing is that you're collating a lot of channels into a fewer set of channels, and then you're passing it through your depth-wise separable 3x3 convolution. And once you have that, again, you are using a 1x1 convolution to regain back the number of channels. Okay, maybe again increase back the number of channels. So it's sort of like a bottleneck structure where you have, say, a large number of channels initially. You're using a 1x1 convolution to reduce the number of channels. Then you apply your 3x3 convolutions, and then again you use your 1x1 to again increase the number of channels. So even though your model, I mean, why do we have multiple channels in any sort of convolution network? So that you get to learn that many amount of patterns in your given data. So by using this bottleneck structure, you're not reducing the number of channels that are, at the end of the day, if you consider this entire thing as a single block, you're not reducing the number of channels that this particular block is processing. But by reducing the number of channels before passing it through a 3x3 filter, you're reducing the number of parameters that you're working with. And again, you're increasing back the number of channels before passing it on to the next layer. So that is something that MobileNet V2 does. And turns out both MobileNet 1 and MobileNet V1 and V2 are able to achieve good enough performance compared to the amount of compression there, or say reduction in size they're able to achieve. I mean, when these models came out compared to the state-of-the-art models, then these were comparable to the performance of the other models, considering the size of these models, which were significantly smaller than the largest models in those times. So these are two very interesting technique of utilizing intelligent design of the network, or maybe intelligently reducing the intermediate input size, so that you can also reduce the number of required parameters in order to learn this particular model. Okay, right? Now, what will happen is that we will now move to something known as neural architecture search, which builds a model, which is sort of as automating the process of designing a model. So you will see that it will try to make decisions like this only. MobileNet V2 or V1 or any other, very such lightweight model design, where sort of hand coded, we had some assumptions based on which we created a model and maybe optimize the structure, make this deploy separable, or making a bottleneck structure. But we all the researchers who created this, they did it in a handcrafted manner. They had some assumptions, and I created a model, and finally were able to justify these designs. What neural architecture search does is automates the process of designing the model itself. So maybe these components will get utilized within neural architecture search itself, but that decision will not be based on any random guesses. That decision will be based on how the model is performing for a given task. If the model does not perform well on a given task, then those design decisions will automatically get optimized and changed. Okay, so that at the end you get a very good model that works properly, at least for that specific task. Okay, so we'll start with that concept now.
Sir,
yeah. Yes.
When we are collapsing the 50 into 10, what techniques are we using? Is it autoencoder?
No. It's a simple 1x1 convolution. So generally what will happen, suppose if you have any input of say H cross W cross 50, if I pass it through a 1x1 convolution and say the number of filters at this layer is 50, you will still get back H cross W cross 50. Okay, because how does generally your convolutional layer reduce the size of your input? If you use a 3x3 filter, you'll not be able to fit that 3x3 filter at every position. So your input, your H and W generally reduces. Okay, and depending on the number of filters, output filters you're using, your number of channels of your output will also change. So what you're doing in this case is you're using a 1x1 filter, which does not change your height and width of your input, but you're reducing the number of, say, output filters for 1x1. Say you reduce it from 50 to 10. So when you pass this particular input through a 1x1 filter of, say, with output number of filters as 10, you'll get the same output size, but the number of channels in the output will be 10. And this is not simply deleting 40 of the channels. This is combining these 50 channels and giving you the most informative, say, a combined set of 10 channels. So just consider what will happen when you apply a 1x1 filter to any two-dimensional structure, two-dimensional input. The H and W will still remain the same.
Sir, 1x1 I understood. That will not change.
Yeah.
But the depth of 50, right?
yeah. So this is actually this is actually the number of output filters. So when you define a convolutional layer, you mention the number of input channels, then the number of output channels, which is basically the number of output filters you're using, and then you say mention the size of your filter and all those things. Okay. So this was the input channel, this was the output channel. Output channel actually corresponds to the number of filters that you're using at this particular layer. So if this was 50 and now you set it as 10, so even though because of 1x1 convolution, the size will not change, but the number of channels, output channels is only 10. So your number of channels is decreasing for that particular input.
Okay.
Okay. Right. So before coming into neural architecture search, we go to a more generic term, which is known as automated machine learning, whose whole objective is to basically automate the entire process of applying machine learning or deep learning to real world problems. So this includes everything. The ideal AutoML, there are a set of AutoML frameworks. The ideal AutoML framework will only take the data from you, the required tasks that you want to perform on that data, and will perform all the operations for you and give you a model that you can directly deploy. That's the objective of the concept of automated machine learning. And if that can be fully achieved, I mean, there are still frameworks that perform AutoML. Such frameworks will actually enable even non-experts to build very good, effective deep learning models for different tasks as per your requirement, right? And obviously, you'll reduce the time required, or maybe say the cost required of say hiring a ML team or something like that. It's still, I mean, you still require teams to come up with good decisions or good set of data that you want to actually train your model on. But the general idea or the goal behind this concept of automated machine learning is to automate the entire process. Okay, right? And some common techniques inside say AutoML might be considered as say an automated hyperparameter optimization. You must have heard of there are some online platforms that actually, I'm forgetting the exact name for those, but you can actually provide them the model and the data set, and they can and mention which hyperparameters you want to tune, whether it's learning rate, batch size, and other factors, and they can actually give you they'll perform sort of a grid search on the entire setup and basically tell you which hyperparameters are best for your given model. Similarly, there's another concept of meta learning, and which basically is also another term for learning to learn. So meta learning has been more generically used in many concepts, but the general idea is still that you're training a model, say, while assuming that that particular model helps in training another more say central model. Okay, so you're learning to learn a model, sort of like that. It's a more generic concept. We may discuss this sometimes later on, but it's another concept of say it's otherwise known as learning to learn. We might look at it at a later stage. Okay, and the thing that we'll cover today is neural architecture. There are also other things that falls under AutoMLs, but we'll basically look under neural architecture search in this particular lecture. Okay, all right. So any model that you take, the architecture is important in that case, because you want to have an architecture that performs well on a particular data. For example, if you consider an MNIST data set, and it's a very small size data set, you only have numbers, handwritten digits in them, and these are very small images. I think 28 plus 28 size. I think they are black and white images, just a single channel. If you try to train a fully connected layer, it generally easily gives you within 10 epochs, it will give you say some 98 or 99% accuracy. But if you try to train a convolution layer on top of this, convolution network on top of this, it will not give you that much accuracy. So depending on the task itself, your type of architecture that you choose will differ. And we, before say any sort of neural architecture search, we were doing this manually. Researchers were doing this manually, making guesses about what would work and what would not work, and then they would try out different versions of their model on different data, and then decide on whether that particular architecture has been designed properly for a given task or not. So this, in general, it becomes harder as you try to maybe look at very large data sets, or maybe try to optimize or make very small adjustments to a network. So if you make a small adjustment to a network, maybe in a particular layer, and then you train a network, you will not be sure that whether that particular change has actually worked that well, or maybe it's just noise or something like that. So you may have to train it for different other architectures, and then maybe run it multiple times with different seed values and other things. So in general, neural networks are very hard to design, say, manually. Obviously, you also need domain knowledge as well as expert knowledge in this field. Okay, and that is what your neural architecture search is, or NAS, is trying to automate. It's trying to automate the process of architecture engineering, or the process of designing artificial neural networks. Okay, and we'll see that how we can basically divide this process of neural architecture search into three components. You have a search space, which will basically define what kind of components that you can build, how you can build your neural network in this particular case. So depending on a use case, you might also choose a more specific search space. For example, if you want to create a fully convolutional network for something less, some task like say segmentation, ideally you don't want to then have any sort of fully connected layers in your search space, because that will increase the amount of time your NAS spends on searching for the correct model. The next concept will be the concept of search strategy, which will decide how you go about picking the next architecture to test on. Once, say, you have tested on the current architecture, how will you pick the next architecture? And finally, you have your performance estimation strategy. Remember this, we are mentioning this as performance and not as accuracy, because generally what you want to do whenever you perform any given task, you might want to have a very high accuracy on a given, say, classification task, or some other, say, IOU scores on your detection task. So, but in some cases, not only performance in terms of only accuracy may not be the only important factor. You may also want to make a model extremely fast. I mean, there are cases where I think the network called Efficient Net was actually built using NAS, where the objective was to not only perform well on the imaging dataset, but also do it with as few number of parameters as possible, wherein your implicit model compression itself comes in. I mean, designing a just like we saw, one of the techniques of model compression is actually designing a lighter weight model. So NAS can actually do that for you without having to test out different weird combinations of, say, networks and all. Okay, and so we'll have your performance estimation strategy that will be discussed as well. Okay, so first let's look at. We'll discuss these three terms and then go into details about these three terms. So search space will define which architectures can be represented through this, can be identified through your process in your particular search. Okay. So we can restrict the type of neural networks that you can actually search for, so that you don't spend too much time, because you're not doing this manually, and algorithm is doing the search for you. So if you increase the search space too much, it's just like saying that I want to find out, say, the number 2. So, and if I give you 1 lakh numbers and it's not ordered and I have to find the number 2, what I can do is that I can say that, okay, I'll not look at any of the odd numbers. Okay. If I don't look at any of the odd numbers, I can simply half whatever the size of your array is, and that reduces your search space by a very large margin. So similar concept happens in search space itself. You can actually reduce the available, say, versions or available components that you want to search for getting a network for your given task. Okay. So your search space will define different types of operations, like, say, convolutions, fully connected layers, pooling layers. You can also have your any sort of your dropout layers and other different kinds of deconvolution layers and other layers. And it will also mention how these different layers can be connected with each other. So that way also you can actually create different types of architecture. Right. So while designing this thing, you will obviously incorporate some prior knowledge about these particular settings. Okay. And if you can do that, you can actually reduce the search space again and simplify the search. Example, what I just said, that suppose you're trying to design a fully convolution network and where you don't require any fully connected layers, you will exclude any sort of fully connected layers from being part of the search. Okay. And that way you can reduce the search space and make it faster. In general, neural architecture search will be a slow process, because you're not just trying to train a single model. You're trying to you'll try out different models with different number of layers, maybe different types of layers in between, and then come up with the best solution for your given task. So depending on your time, you may also maybe exit a bit early and come up with the best model at that particular time, whatever. So you ran this process for, say, 5 hours, and then whatever model you get, you just stick with it and go ahead with it. But then the longer you run your neural architecture search, the better chance you have of getting a much more optimized model for your given task. Okay. So obviously, another thing that will come into play is the concept of human, any sort of bias. Suppose if a person likes to always utilize, say, through 3 fully connected layers at the end, or say, he always likes to utilize blocks of bottleneck layers that are present in MobileNet, which may reduce the number of parameters for you, but in a way you're trying to take an advanced decision on behalf of your NAS algorithm, even before your NAS algorithm has actually started searching. So some sort of biases may also creep into at least the basic building blocks that you're trying to include in your search space. So there can be ways of preventing that as well. You include different types of experts while designing your search page itself, so that any sort of single bias does not affect your search page. The next concept, as we mentioned, was the concept of search strategy, which will basically decide how will you search the space, which will obviously be extremely large. You can have, say, you can bound the search space, but you will still say, I can have at least 2 layers of convolution layers, or maybe at max 10 layers of convolutions. But then within that convolution layer, the number of the filter size, the number of input, the number of output channels, the number of strides, the number of padding, all of these can vary. And as you can see, if you try to apply all combinations, this is a very large space, okay, which is obviously very difficult to search. So you'll have to, there are various strategies of coming up with, say, a faster search. There will be some greedy approaches also, so that you can quickly arrive at a solution. And there are some longer approaches which will take obviously longer time. Okay. So you will obviously face this dilemma while using any of these strategies about this exploration and exploitation. So you might want to get well-performing architectures very quickly, but then there's no guarantee you'll get the most optimized one. Okay, so you might come up with a suboptimal architecture which will not fully satisfy your problem, because if you were already satisfied with suboptimal architectures, you already had handmade architectures like, say, your ResNet, DenseNet, and others. You came here only because you wanted a better architecture. So it's you should spend more time into this while performing this search. Okay, but then it depends upon your the priorities of that particular team. Okay, the third component is the performance estimation strategy. Okay, and generally you'll have some sort of an unseen data on which you will try to evaluate your model. Okay, so evaluation can be through different metrics. You can have accuracy, you can have biasedness of your, say, model, or some other factors as well. Okay, right. And obviously the simplest option is to perform, given that model, you perform a simple training and a validation of the architecture on that particular data. But then this will obviously be very computationally expensive. So we'll see some very basic strategies of how to make this process faster. Because suppose if I have to train a model, I'm building a model for ImageNet, which is a very large data set. It has around, I think, so it has 1,000 classes, but number of images, I think, are close to around 12 lakhs or something like that. So if I have to test out different models, after training them fully on this entire data, it's going to take a very, either it's going to take a very large amount of time, or it's going to take you that amount of, say, if you have a large GPU memory, so maybe you can increase the speed of this process, but then even then you would require a lot of computation power, as well as even with that, you might require a very large time for identifying these things. Okay, so there are many research, they are trying to reduce this cost or time of these performance estimation techniques, and which is why, even now NS is comparatively slower compared to any, say, handcrafted design, which is obvious because you're trying out a lot of models. So it's a trade-off. So depending on your requirement, you might choose to go for NS, or maybe you can go with any of the standard off-the-shelf models that are currently up. So we'll see some of the techniques, not all of them. And so you can have something like called a cell-based search space. We'll maybe discuss this idea in much detail. You will have search strategies, different types of search strategy. We also have something known as a random search strategy, which basically tests out different models randomly, and whichever model you get the best performance at a given time, you basically save that model and keep performing a random search. But then there's no guarantee that you come up with an optimized model in this particular case. So you also can look at other types of algorithms. And for evaluation method, the base method is simply you perform full training followed by full testing. But that will be extremely slow. We'll see other techniques that can make this process much faster than it actually is. Okay. Now, this will be the general way of performing neural architecture search. You'll have some search space defined early on, which will decide which kind of models you can actually, which can actually build. You have your search strategy, and you have your performance estimation strategy. So your search strategy will actually pick one of the models from, or maybe a component from your search space, and then it will send the entire architecture to determine the performance. The performance gets evaluated, and based on, say, some metric, whether it's accuracy or something, that particular performance metric goes back to search strategy. And based on whatever performance, how this architecture performed, the search strategy will decide whether to keep or not to keep that additional component or additional hyperparameter that it just added. Okay. So this process continues, and ideally, it's very difficult to come to know when your process is actually ended. So you might keep on finding minor improvements as you run your model. So generally, what you do is that you run it for say 1,000 trials, or say some fixed set of trials, and at the end of the trial, whichever is your best method or best model, you take that. And you might also place in another condition, so that, such as suppose you have already run a ResNet 50 model on that particular task, and you already know the test accuracy or the validation accuracy for that ResNet 50. So you can run your trials as long as you don't beat that accuracy. That can be another approach too. So you can do it as preferred by you, do the search as preferred by you, but there will not be any defined endpoint. So you will have to come up with a strategy to define your own endpoint, maybe endpoint in terms of amount of trials you have done or the amount of time that you are spending on this particular setup. You can define your own endpoint and continue the strategy. Okay. So we'll look at the concept of a search space, and we'll see a very basic search space first, and then maybe extend it to a more sophisticated search space. Okay. So a very simple example will be a chain structured neural network, where you have a set of layers which are basically sort of connected in a feed forward manner. Okay. And that in such a case, your search space will get to choose the type of layers at every level. And I mean, whether to add a newer layer or not, whether to stop at a particular layer or not, and maybe also change the intermediate parameters of these given, say, layers. So if you have a convolution layers, you might want to change the say the size of the filter, the number of output filters, the stride padding, and other such factors. So a chain structured network architecture can be written as a sequence of n layers, and the ith layer will receive input from the previous layer, the I-1 layer. Okay, and the output of the ith layer will serve as an input for the I+1. So it's a simple feed forward sort of a connection. Okay, in such a case, you will have the following parameters that you'll have to learn for this particular setup, which is the maximum number of layers that you want to add. So if you don't restrict the number of layers, maybe you don't want to restrict, you want to run this particular setup for as long as possible. So your searching algorithm might keep on adding new and new layers, provided the performance is also increasing. Okay. And also the type of operations that you want to perform at every layer. So all of these now are generic blocks, and each block can be replaced by, say, a pooling layer or convolutional layer, or say some more advanced operation like, say, depth-wise separable or dilated convolution. So you don't have to create your entire mobile net structure. Maybe if you want explicitly, you can give it the components of your mobile net, and it can give you a good structure or good positioning of these individual components, so that you get, say, a very good accuracy. Or if you also set the the target to not only improve the accuracy but also reduce the number of parameters. So then given, say, an option between convolution and depth-wise separable convolution, your NS algorithm might choose a depth-wise separable convolution. Okay. So this will happen automatically. You don't have to design your own network as such. Okay. And obviously, these things also will get tuned. Your hyperparameters like, say, number of filters, kernel size, and others for your convolution layers, a number of units in your fully connected networks, and other factors which are anyways part of every layer. So these hyperparameters will also get tuned, and your NS will return you the best possible set of these parameters for you to train your model on. Okay. And obviously, the parameters which are on 3, which is the hyperparameters, are associated with the corresponding layers that you have added in each of these levels. So based on that, your search space, it will basically be structured in this particular manner. Okay. So it's a very basic search space where you only get to sequentially add new layers and change the type of layers, or change the hyperparameters of each of these layers till you reach your output. A more complicated version will be to allow maybe more combine these intermediate layers in not just a single feed-forward manner, but maybe have different branches and other skip connections and etc. In your network itself. So in this case, if you generically define the input of any given layer I, it will be a function of all the previous layers. Okay, you may choose to ignore all the previous layers, or a simple chain network, which was there in the previous case, your chain structured neural network can also be achieved from this particular setup. You simply ignore everything else, and your input basically becomes your output of your previous layer. Okay. So this gives you a lot of a lot of power in the sense of coming up with more complex architectures. You can combine not only sequentially layers, you can also have them parallelly, so that you can get the best out of the given output. And special cases would be, again, as I mentioned, will be a case of chain structure network, which is basically simply looking at just the previous layer for your input. Okay, it can be residual networks because there are skip connections. If you have seen the concept of ResNets, what ResNet does is that you have a set of layers. The concept of ResNet came in because you were not able to make your CNNs any further, any more deeper, because you're suffering from something known as vanishing gradient. So deeper you make a network, there's a chance that after a particular phase, the initial networks do not get trained much, because the gradients, when they're passing through all of these layers, become very close to zero. So what ResNet did was that he added something known as skip connections, which allowed the input as well as the gradient to bypass some of the layers. Okay, as a result, you were able to build much deeper layers, like say ResNet 150, ResNet 100, and so on. So given the option of creating a skip connections, you can give that option to your search space as well. So NS will be able to put in place skip connections as well between layers, and as a result, your input will be not just the previous layer, but maybe a sum of the say 2-3 layers that are before it, or maybe 2-3 blocks that are before it. Okay. And you can also have even much more further complex networks, like say dense nets, where you actually take all previous layers output and concatenate them and then pass it to the next layer. So this is sort of like you're allowing all of these options to your network, because you are allowing multiple branching, you're allowing skip connections and other things. So NS will try out different types of these combinations, and whichever is the best, it will keep that saved separately and will continue your search for you. Okay. And as already evident, this is going to take a lot of time, because all of the search will spend that much amount of time searching through these things. So up to this level, we have been dealing with individual layers at each level. Okay, so a convolution layer, pooling layer, dropout layer, whatever. Okay, which in itself becomes a bit tricky to design, because that will take that many amount of trial and errors to remove. Say if you're considering a 50 layered network, you can have that many types of and suppose at every layer you can actually add either a convolution layer or dropout layer. So you have say 5 or 6 combinations. So you'll have a 6 to the power 50 such scenarios of different types of layers that can happen, and that will take a lot of time. Okay. So the other option is to come up with something known as blocks rather than layers. And this is such a space is also known as cell search space, which is that this architecture in this case will consist of repeated blocks, and these blocks will get added in this manner and connected in this manner, rather than individual layers that you add or delete one by one. Okay. So instead of considering one layer at a time, we'll consider say a block of layers, and we'll try to add these blocks one after the other, or maybe parallelly, or maybe with skip connections or whatever like this. And this also aligns with handmade architectures like say ResNet, which also has some ResNet blocks. And in ResNet blocks, you actually have skip connections that are connecting, that are actually skipping blocks rather than individual layers. So cell space actually allows you to, it also reduces your search space in that manner. You're no longer looking for individual individual layers. You're basically looking at how to combine different blocks, which already has a set of say type of layers already in it. Okay. That streamlines your search space, and it makes it also faster. So you generally look at say, if you are solving a difficult problem, complicated task, you'll generally go for a cell search space rather than say a simple simple layer-based your architectures, search base. Okay. And generally, there can be two types of cells. You can have a normal cell that does not change the dimension of your input. So maybe a set of convolution layer which simply processes the input, and the output size is actually the same as your input size. Or you can have a reduction cell which reduces your dimension. So you can have, say, a lower. So as you go down, you might require a set of normal cells, and then you apply reduction, so the size decreases, and finally you can add a fully connected layer at the end when the size has decreased enough, and that will give you your classification head or whatever you have. Okay, so different ways of combining the blocks will be used. Again, your skip connections and other things will still be there, but you're no longer working at very layer by layer level. Instead, you're looking at a block of layers level. Okay. So final architecture is built by basically stacking these architectures in a predefined manner. So it's either you apply only in a feed-forward manner, or you can allow, say, branching and skip connections and others. Okay. So this is again the same cell. Okay. Next is the search strategy. So there can be many ways of basically identifying which architectures to test. That can either be, say, random. You can have something known as Bayesian optimization, evolutionary methods, Adel methods, gradient-based methods. The paper that made search the NS popular was based on NS, reinforcement learning. This is actually a paper by Google, I think in 2017 ICLR. I can provide the name of the paper, and which basically performed NS using reinforcement learning. Okay, and we'll discuss these basic strategies. We'll not try to go into too much depth, because these in itself are separate topics in themselves. So evolutionary methods or reinforcement learning, these are separate courses in themselves. So we can't go into that much of detail. We'll just look at the overview of these methods. Okay. So if you have some idea about the reinforcement learning problem, you know that reinforcement learning tries to solve a problem by considering agent. If you have looked at the artificial intelligence course, you had the concept of agent, which performs, say, a search in a complex search space. You had some search trees, and you performed some kind of, say, DFS, BFS, or other some more complex search, A-star search and all in your search space. So even in this case, you have a search space, and you can consider the process of finding the best model as your goal in your search space. And your agent is trying to find the goal as soon as possible, as quickly as possible. So that particular setup can be considered in terms of an RL problem, where generating a neural architecture can be an agent's action, but whether that architecture that you get is actually good or not, that will be provided by your performance estimation, which actually gives you the reward to your model. So if you get a good model that has, say, the best performance up to this point, you will give it a higher reward, so that it's more inclined towards giving you models that are similar to that and which are getting better performance. Okay, right? And that's what's mentioned over here. The agent's reward is based on the estimate of the performance of the trained architecture on your unseen data. Okay, so you can model this particular setup in terms of a problem like that. Evolutionary algorithms it's a more interesting concept. It basically, what it does is that you instead of maintaining one good model, you maintain a set of good models. Just like, say, a human population, you have, say, not just a human population, any sort of population of, say, initial, say, chimpanzees or other animals, and you generally have a large population of samples, and some of them are maybe more fit, some of them are not so fit. So when the next generation comes in, the fitter tends to represent more of the next generation as compared to the not so fit ones. So in a way, over time, the set of population that you maintain will ensure that the models that are not so good will get weeded out slowly, and you have a set of say, architectures which are performing well. And you apply, whenever you move from one generation to the next, you try to add some mutations into these models, maybe change one layer, maybe delete one layer, maybe change the hyperparameters of a particular layer. So there is some mutation. This is a way, in this way, you're trying to actually replicate evolutions. That's the objective of any evolutionary algorithms. But a difference from standard search strategy will be that you will keep a set of trained networks, other than, say, a single network that you're trying to test out always. Okay. Right. So in the context of new NAS, you'll apply mutations by maybe adding or removing a layer or maybe altering hyperparameters of a layer. That way, you don't have to think about which network to test out next. You already have a set of networks that you're maintaining as a population, and from those set of networks, you're trying to edit that networks a bit. And if after that edit, that network is better, you keep it. If it's not better, it will not get to it will not go too far down your iterations. Okay, so that way you add and delete to your population, and the goal is that after say a period of time, the population of networks in this case that you have are very good networks, robust networks that can maybe solve your problem for you. Okay, right. Another very simple and greedy approach is the hill climbing algorithm. You basically take a basic architecture first and you make one edit to it, and if that edit improves the performance, you keep that edit. Otherwise, you discard that edit. You try another edit. So it's also known as a greedy. It's a hill climbing. It's a local search algorithm. Those people who have done the artificial intelligence course, I think that is part of your curriculum as well. I think at least for some of you. So that had that concept of which is a very straightforward greedy concept. You simply make a simple edit to your network. If it performs better, you keep it and try the next edit. Or if it doesn't work better, you discard that edit and maybe edit some other layer or edit some other property and keep on searching and do it for maybe say a fixed period of time, and whatever model that gives you that best performance up to that given point is your resulting architecture that your NAS is returning. Okay. Finally, we have the performance estimation strategy. Again, we have to do some sort of a performance estimation based on unseen data. We can look at the accuracy. We can also look at other properties as well. Okay, and this is important because on the basis of this performance itself, your search strategy will decide whether to keep that current model, modify that model, or maybe discard that model altogether and maybe start a fresh search or something like that. Okay, so this portion is that's why very important, but also since you have to perform a performance estimation, maybe you train your model on a given data and then evaluate on the given say validation set. This becomes a bit tricky because it will take a lot of time in order to perform this performance estimation, because you'll have to train a model. If you have a large data set like say ImageNet, that itself is going to take up a lot of time. And at the end of that entire process, you still have to maybe discard that model because that model may be not performing that well. Okay. So performance can be measured in terms of say accuracy, inference time, model size, or any other metrics. You can also combine these matrices. For example, if you look at the efficient net architecture, it was actually designed using NAS while keeping in mind both your accuracy as well as your size of your model or the number of parameters that you're introducing in your model. So that way, efficient net, if you look at, I think some of the resources online, you'll see that it can achieve higher performance on the ImageNet dataset while requiring much less number of parameters as compared to say ResNet or say other handcrafted networks. Okay, right. Again, as I mentioned, this is a very costly process, either in terms of time or in terms of computational requirement, and it will require a lot of time because you have to train a full model maybe on a difficult task that takes time, and then again maybe you have to discard it and try another model. Okay, so we can achieve some sort of a speed up by applying some tricks like that. You can try training the network on not the entire data, maybe a subset of the data, or maybe a downscaled version of the data, or try it on say you reduce the number of channels at each layer before you actually train that model for that particular setup, or maybe you train for a fewer epochs. These things will still work because you are fair with all the models that you test. You'll not change, say, if you're only testing the models for 10 epochs, suddenly you'll not try testing a model on after training it on 100 epochs, because that will be unfair with the other candidate networks that you tried on. So you'll try to maintain that consistency, but this is some trade-off that you're making in order to speed up this process. Okay. Another can be that you train, just like this, in case you are training for a few epochs, but you have some mechanism based on some expert knowledge that you can extrapolate that performance. Suppose you know that if you train network on MNIST, within one epoch, you get close to 80% performance. Now, suddenly, if you come up with a network that after one epoch only gives you, say, 50% performance, you know that something is wrong. This network might not work that well, and maybe you add in some of this expert knowledge into this process itself to make the process a bit faster. Another approach can be that instead of training every model that you get from scratch, you may inherit the same weights from the previous model that you tested. Only the layer or the block that you just changed now, that model may be kept as unchanged, and then you start training, so that your training time may be the convergence of your training must be much faster. Okay, so you can try out such techniques like this. These are mostly heuristics and based on some domain knowledge if you have of training deep learning models, and based on that you can actually speed up these techniques. Okay, and these are some of the frameworks that are available. I was trying to run the auto PyTorch setup, but it's not getting set up. So I'll show you a brief example on auto Keras, which let me just switch to this particular tab. Anyways, I don't need to run now. I have already run it. So this is a very simple way of starting off with CNS, and AutoKeras is a library that's provided by Keras, which falls under your TensorFlow. And this is a case of building a, say, image classifier for your MNIST data. I have reduced the data so that I could run that particular setup very quickly, but ideally you train the thing on the entire training set. And in this particular case, I'm not giving any sort of additional information. It has a set of information about which search page to use, and what kind of layers you want to use and other things. And the only thing that I mentioned is the maximum number of trials is 3. Okay, so number of architecture you will be basically trying this NS for, and based on that, it gave say this particular architecture, which had a input layer, normalization layer, 2 convolution layers, max pooling layer, dropout, flattening layer, and again a dropout, and finally your fully connected layer followed by, say, classification head. Okay. So this was a very basic way of. I'll release this code as well, so you can experiment with different types of hyperparameters. The other approach was to basically apply at least some restriction on the search space so that your searching becomes faster. So we can actually mention the type of blocks. You can refer to the documentation of AutoKeras to see what kind of blocks you can give. Over here I just mentioned, say, a ResNet. So in this case, it will try to find out the best ResNet architecture itself, which will work best for this particular setup, which is sort of defeats the purpose. But okay, for an example use case, I have just done that. I have set the normalization to true. I've changed the data augmentation to false. I mean, this falls under hyperparameter optimization, but we can consider this as part of neural architecture search as well, because it directly also affects the type of architecture you pick. And then again, we set some max number of trials, and based on whatever network that comes out to be best. So this one was trying out, I just gave one trial, so it just tested out the, I think the ResNet 50 architecture. I don't seem to find it. Yeah, ResNet 50 architecture, but you can also try out, say, some other types of models. Okay, so I'll release this code. You can refer to the code, as well as you can refer to the documentation of AutoKeras. If you want to maybe train or test something out, you can do that. Okay, any doubts? It was a long session. Any doubts in this particular part?
Sir, in this NAS, can't we, like, is it only possible to try with architectures that have been already done? Can't we use from scratch?
No, you can do that. This you can. In fact, the first one that if you look at the first example, it actually uses very basic convolution layers only. Convolution layers, max pooling layers, dropout layers, and fatal layers. So you can actually specify what kind of blocks you want to use. In this case, I just wanted to run this a bit quickly, so I simply mentioned block type as ResNet. So it utilized the entire ResNet network itself. You can mention the type of blocks. There are other options, I think. You can refer to the documentation for it. And you can use, I think, residual blocks, which are components of ResNet. You can also use other components, or maybe you can also customize the blocks that you want to create. So you can create your own set of, say, 3 fully connected layers and consider that as a block, and then ask your model to only utilize blocks of that type. Okay.
Sir,
in general, this process takes a lot of time. Yeah.
Sir, can we use this to, like, also create some novel, architecture? So is it like
Yes. Yeah, definitely. You can create a novel architecture. Suppose you have your own requirement of a kind of data, and you mention the type of blocks or the search space that you want to build your network on, and you put some restrictions. So, for example, in this particular setup, I think your image classifier only looks at the validation loss. That's its only objective is to reduce the validation loss. So you can put in some additional constraints. You can say that you look at the validation loss, but you also look at the training time, you also or the inference time or the number of parameters. So whatever such criteria you provide, you will get the best architecture that satisfies all of these constraints and performs best for, you say, if you do it for 100 trials. So whichever model performs best in this 100 trials, you will get that particular network as your output. And obviously, if you train for more number of trials, you'll get better results. But there's no fixed ending time for you. It's only determined by how much time you're willing to spend on this particular search. Okay. Okay. If there are no other doubts, we can continue tomorrow for our next lecture. I'll just stop the.
Sir, I have a question. Like, for example,
Yes.
is this usually used where we have, let's say, a rough architecture that we already have, and we are just trying to adjust the layers or some blocks? Is it useful in that respect?
You can, yeah, you can do that. I mean, I'm not sure if AutoKeras allows that level of changes, but I mean, by definition, yeah, neural architecture search will allow you to modify an existing architecture as well. So what you're basically doing is that if I already give you an initial architecture and then ask neural architecture search to optimize it, it is supposed to do that as well. Because at the end of the day, you're trying to modify at the core of it, modify every layer, unless you till you get your best performance, or maybe till a few set of trials, and among those trials, whichever is your best performance, you get that. So I'm not sure how Keras does that internally, or maybe if there's an option to do it in Keras specifically, but I'm supposing they have that option. We'll have to look at the documentation a bit more detail to tell you that.
So, in your experience, AutoML does it more conveniently, I guess.
So AutoML will give you, say, your best architecture. For example, as I mentioned, you have a lot of architectures nowadays like EfficientNet, which is designed using NAS itself. But it then depends on how much time you have, or how much computation you have, or how much time you're willing to spend, rather than going for a handcrafted model, say ResNet 50, which will work for most of your day-to-day tasks. It then depends on how much time you're willing to spend on that.
Okay, sir.
Okay. Okay, I'll stop the recording.